If you remember in the last video, we were comparing classical and empirical probabilities, and we found that they weren't the same exactly, but they were very close to each other. And that the longer you let the probabilities or the experiment play out, the closer that the two probabilities are. That's why casinos try to keep you there so long. So suppose you want to run an experiment many times, but you just can't physically do it. You don't have the time, you don't have the money, you don't have whatever it takes. So that's when we use mathematical or physical models to reproduce the conditions of the situation. For example, you toss dice or things like that. Or you can use computers to do it for you, which is the way probabilities in the upper levels have been going for a while. So if you simulate what's going on, that allows you to study situations that are impractical or dangerous to study in real life, and they save time and money. So for example, I've seen this happen with running simulations for traffic patterns. So they want to see what an accident will do to the traffic flow. So you say, if we have this accident, what are the chances of this other accident happening, something happening over here, et cetera, et cetera. So it would be dangerous to do that in real life, but you could do it with a computer simulation. So suppose it takes you 2 seconds to perform each single toss of the die. How long would it take you to, each single toss of the coin and die? So how long would it take you to perform the experiment of tossing a coin and a die 1,000 times in seconds, in minutes and hours? Well, okay, so you take 2 seconds times 1,000, that'd be 2,000 seconds. And then you divide that by 60 for the minutes, and you divide it by 60 again for the hours. So let me see here. You already see how this goes. So you take 2,000 seconds divided by 60 seconds per minute. That'll get you 33.3 minutes, and that's 0.56 of an hour, which you don't have that kind of time to toss coins and dice around, right? Nobody's got that kind of time. So we're going to have to make a computer program do it for us. So I have the computer program StatCrunch here, and I have it's conducted the experiment of tossing 1,000 tosses in mere seconds. And just for fun, I'm going to show you how to make StatCrunch do something like this. It's pretty simple. So I have my sample space right here. You can see it. And then I'm going to toss into variable 3 my data set. So I got a data. I'm actually going to do sample, not simulate, just because of the way this program works. So I'm going to go from sample space. I want a sample size of 1, but I want to do it 1,000 times. And I'm going to store it. Well, let's see. Compute. Oh, it did it that way. Whoops. Hold on. There, I finagled around with it and got it all into one thing so you guys can see it. So this is our simulation here. So I've got, my first toss was T2, my second toss was H3, and so on. And then I would want to count how many were H1 from this entire data set. And it just so happens that there were 100 H1s in here. I counted it up with Excel. So the number of H1s was 100, just in case you were curious. So that's how you do it. You make the computer do it in mere seconds. It can run all sorts of calculations for you, and that's a simulation. It allows me the time and the effort, or saves me the time and effort of having to do it. So for example, here, I had StatCrunch do it 1,000 times, and I'm showing you the first 15 rows right here. And the number of H1 on this particular example was 94, because that's just the way it worked out before. So if there were 94 of the 100 tosses, that would make the probability of H1, oops, hold on, make this go away. 94 out of 1,000, which would be 0.094. Great. Well, why isn't that answer 0.083, which is what we expected from the classical probability? And, well, there are a lot of good reasons for that, but you wouldn't expect it to work out for the same reason that you don't expect it to work out when it's empirical, right? It's not the same as your classical probability, but it's going to be close. And it should hypothetically be closer than your empirical probabilities were, right? So the classical was 0.083, your empirical was 0.094. So it's close. It's closer than our earlier results for 30 and 60 trials. And the larger the sample space, would make it closer. Oh, I should say a larger sample space would make it even closer. If I did it 10,000 times or something like that, that would make it even closer. So that's what a simulation is. It's basically computers being used, or sometimes dice or other things, but being used to simulate something that you don't want to have to repeat yourself, either because it would take too long or because it would be time-consuming and dangerous. Now, there is one last kind of probability to talk about that doesn't really take any time at all, and that's the subjective probability. Now, subjective probability is a probability that is obtained by using personal judgment. So most of life's events are not repeatable, in which case the subjective probability plays a part. When you look at this mountain, you're saying, what are my chances of making it up this mountain? You don't know, because you've never climbed that mountain before, and you'll probably never climb it again. So you have no data to base anything on, so you can't make empirical. And you have no cards or dice or anything, so you can't do classical. So that means it's subjective. You have to say, I think my chances of making up that mountain are 60%. Why? Because I think so. You're making a personal judgment. Keep in mind, however, that subjective probabilities are perfectly legitimate. I make fun of them a little bit because often they're not legitimate, but they can be, or often, I should say, are frequently perfectly legitimate and are sometimes the only method of assigning likelihood to an outcome, because what you're doing just doesn't have a repeat possibility. If that's the case, then this is all you've got. So, for example, what are the chances of Brad Pitt ever winning an Oscar? You'd make a subjective guess, right? And some people would be making a very wise guess, like if they're big in the industry or whatever. But if they're not big in the industry and they're just guessing, then that's less legitimate, right? So it just kind of depends on the person making the guessing as well. All right, so let's suppose during the World Series of Poker broadcast on ESPN2, which is very fun to watch, I highly recommend it, they flip over their cards, and then on the screen it'll show the person's percent chance of winning with that hand. So you see their cards and they say 88% chance right by their name on the screen. What kind of probability is that? And that is very much a classical probability. They have a computer basically that sits there and knows, oh, he pulled up a 7 and an 8 of diamonds. That means this is his chance of winning, or her chance of winning. So it's a classical probability. It's totally based on cards, gambling, everything equally likely. All card hands equally likely, right? Now, what about the probability that the Red Sox will beat the Yankees in their next game? Well, you have some past data, but the thing about it is that the lineups are constantly changing, the workouts are constantly changing. It's not exactly the same. It's not the same as in the way cards are the same. So this is actually more a subjective probability. So when the ESPN people get on, they say, well, the chances of the Red Sox winning this time are blah, blah, blah. What they're really basing that on is their personal judgment. They've been watching the team practice. So-and-so is out with an injury. So-and-so is back in, et cetera, et cetera. It's raining, it's cold, it's not cold, et cetera. Because all those conditions are constantly changing, you're unable to completely replicate every single thing about that game, which means it's a subjective probability. All right, now the probability that the next person that walks into the Red Cross will have a blood type of O negative, which is something Red Cross really likes to know about because O negative is a universal donor. That would be an empirical probability. So what the Red Cross does is they actually track the people that donate blood and the people that have blood drawn and taken in the hospitals. And they know that in a particular region, it's this percent O negative, this percent A positive, and so on. And actually, if you ask the Red Cross, they will give you the numbers that they've got because they track it so carefully. They track it from region to region. And therefore, they know, hey, if you walk into the hospital in Jackson County, they know your chances more or less of you being O negative, you being AB positive, and so on. They have data records to base that future person walking in on because they need to. Otherwise, they would run out of the types of blood that they need. And at the end here, I have a little XKCD comic, which is very generously, they let us post here in the notes. And it just shows you how this was kind of sad. The person that makes this comic had this real life situation happen, and they had to make a medical decisions for his significant other at the time um, about her medical treatment for, I believe it was cancer. And they were looking at prognoses of 81%, 77%. Those are probabilities. They're to some extent empirical probabilities because they're looking at, her gender, her age, her health, et cetera, and they're making, diagnoses and saying, hey, you have an 81% chance of surviving 5 years. And the person that makes the comic said, probability used to be my favorite branch of math because it had so many real life applications. And that's something to keep in mind. Probability can seem very divorced from real life because it seems like it's all gambling and stuff. And it is gambling, so it does have that effect. But it's also more than that. It's also medical decisions. Prognoses, when you're given those percent chances of survivals over time and such, that's all probability. And so it's very much tied in to what we're doing in this chapter, indirectly and directly. Those are generally empirical probabilities, but we all have to make those medical decisions for ourselves or our loved ones later in life. And so probability is perhaps more prevalent in your life than you might realize, even if you're not a gambler like me. I'm not a gambler either. All right, we're all done with section 5.1. I'll see you back here for 5.2.